Right, so let's start going through the ICPC Online Preliminary Contest problems from last year, from 2022. And we'll start with question number two. Question number two, the title was Closely Linked Mammals, Dolphins, and Humans. Um, and there's a lot of problem detail. An important part of competitive programming is just figuring out how to go about reading a problem, because there's a lot of, especially in contests like the ICPC, there's a lot of detail which you really don't need to solve the problem. And so it's very important to highlight in your mind, or maybe actually physically, the key details. So this is a great example of that. If you read the first paragraph, dolphins are sea animals which are classified as mammals and not fish. Dolphins are warm-blooded like all mammals do, which isn't, completely accurate grammar. But um, if you go around reading this whole paragraph, you'll see that this actually has nothing to do with the problem. It's just talking about dolphins. And then you can go to the next paragraph, and even then, that starts connecting to the actual problem. The real gist of the problem is around here. So a unique characteristic of dolphin genome has amazed scientists. Instead of 20 amino acids, it contains 26 amino acids, which are letters represent like capital alphabet letters. Okay, and the sequence and identity of the amino acid sequences matters, but some of their amino acids can morph into other amino acids at will, but retain the function of the original amino acids. And this is somewhat giving an idea. And the most important part of the question is usually towards the end if it's a very long question, and sometimes it's the very beginning if it's a short question. You are provided a list of proteins that might or might not be substitutes, as well as a list of equivalent amino acids. You must check to see if the proteins in each pair are equivalent. If two proteins have the same length and each of the first protein's amino acids can be converted into the corresponding amino acid of the second protein using the available sequence rule at least once, they are said to be homologous. And this, again, a lot of the times what is exactly being said is not going to jump out directly, which is why it's important to reread this a few times. Eventually you'll understand what the problem is asking for, but even then you should try to go over it once more, because there's often a lot of detail, or like small little details that we end up missing, that can also cost us a lot. In fact, I have a very practical example from this. So, and we'll get around to that. But this question is basically saying that we're going to be provided substitution rules. And, just jumping ahead, the input has the substitution rule. So it's saying that C can also be T, and D can also be C. I can be R, and R can be I. K and P can exchange. O and C can exchange. And so this is showing how one amino acids, these are just amino acids, they can convert into one another. And then afterwards we'll be given two strings, and these strings represent proteins. Proteins are just strings of amino acids, and we have to say, okay, is this equals to this? And now the one obvious condition is, okay, if they're exactly the same, then they're equivalent. But the other case which is relevant to this problem is there a way to convert this into this? So for example, this is NaC and this is NOC. So N matches, C matches, O and A do not match. And so the question there becomes, okay, is there a way for me to convert A into O? And so what I can do is I can check my list of substitution. So C turns to T, I turns to R, K turns to P, O turns to C, R turns to O, T turns to E, T turns to F, S turns to H, W turns to P, and F turns to S. There is no mention of A here at all. And so what that would suggest is that there's actually no way to convert NaC into NOC. And that is the actual answer. So if you look at the sample output, there's a no. And if we look at, let's say, the fourth one, so the fourth one is this. So you see, but right off the bat, they're not equivalent. But we can ask, okay, is there a way for me to convert this F into an S? So we're trying to convert our F into an S. And so we can go through a list of substitutions, and we can see that, okay, there's an F here and it does substitute into an S. Okay, that's great. So the first letters can be made to match. What about the second pair of letters, which is F and H, right? So if I look at it just like at a glance, F can turn into S and F can turn into T, but F so far can't turn into H. What's important to note here is F can turn into S, right? And S can turn into H. So there is a way to start from F and end up at H. And the main uh, like challenge of this question is going to be coming up with an algorithm that lets us start with a specific alphabet and then find out which substitutions can I go to from there. And then from those substitutions, I have to ask, okay, where can I go from there? And then from here, I have to ask, where can I go from there? Up until I reach my target. So either I reach my target variable, for example, in the first case, it was S. So either that happens or there's nowhere else left for me to go, or like if I go anywhere, I'm just in a cycle. That's also important to note. Like one case is that okay, you go from here to here and from here to here, and you know, eventually you run out of paths and there's nowhere else for you to go. But the other case is that uh, this node, so this node can turn back into this. So we also have to prevent cycles. And the really common algorithm that we use for this type of problem is depth first search or breadth first search. And the solution I'll show is it makes use of breadth first search. And then lastly, before we go to the actual code, what's important is this aspect I said that when you read a question, make sure to reread it to just check that you've picked up on everything. So what happened to us when we were attempting the competition was we kind of missed this line, which said that a protein sequence contains at least 3 and at most 20 letters. And that is important because if you look at this one, ACBC, or not, is it ACBC? Um, let's see, one second. Yeah, so this is a new test case and this has a new set of substitutions. So A can turn into C, A can turn into B, right? So technically, this A can turn into this B, which will make the two match. But the problem is the length of this is only 2 characters. So that's why we can't do this. So this is a no. Similarly, because this is like less than 3. Similarly, this was way too long. This was more than 20, which was why that one was to be excluded as well. So these are the smaller things that you have to look out for. Now let's just go over the code. And the code is honestly it's a bit poorly written in terms of it's probably not the best way to and the most easy to read way to write code, but this was what just ended up coming about while we were in the competition. When you notice in the competition it gets hard to write good clean code. It's best if you can make your code as simple as possible, but when you're dealing with problems that are like challenging, it takes some effort, so it's all right. But don't create a program that is impossible for you to debug. That's probably the most important thing, right? So when we wrote the code for this program, so we defined some functions. Initially we just took an input of how many test cases there are, uh, and then for each test in the range of test cases, we took a map1 and we took a map2 as input. Basically what that does is that it took this whole line and this whole line and created two lists out of this called map1 and map2. And so it just made this whole thing a list of letters because there was also a dot split there, so just broke it into a bunch of letters. And I did that with the second line as well. Then we pass this to a function called create dictionary dict map1 comma map2, right? And the way this function worked was that it created a dictionary. Initially it's empty, and then it goes through each index and it says that okay, map1 index 0 should have map2 index 0, right? So what that's saying is I'm going to create a dictionary which says, okay, there is an key C. So dictionary, that's a store key value pairs. That's what's important. And so we store a key which is C, and we say that C can turn into the following. That was the goal of the map. So C can, well, firstly, it can turn into T, right? And as we go later down the line, we'll also see that C can turn into O. So that's why in our value, we're going to store a list because a character can turn into multiple different characters. So that's why we're making use of a list. We can't just say, okay, C turns to T because C can also turn into O. That's why for each key, we associated a list, which is the possible substitutions for a letter, right? Then we just wrote some code to handle that. Uh, you can read this if you want. That's, just surface level details. Now what we did was we asked, okay, how many strings are we going to get? So we're going to get 5, and we just inputted them one by one. So the first pair of strings is KROC and KROC. So we just stored that in S1 and S2. And initially we did the length checks. So firstly, for the proteins to be equal, they need to have the same length. But also, as we read in the note, the proteins must be at least 3 letters or at most 20 letters. So we added that validation as well. Then we go through each position of the string. And the point is, okay, we ask, is there a way for me to turn this into this? Then I ask, is there a way for me to turn this into this, this into this into this? And if I make it to the end of my string and I'm able to convert everything, then that means that this is like the two strings are equivalent, the two proteins are equivalent. So that was the point. Now the way to check if we can convert, so the initial thing is, okay, they might already be equal. If they're not already equal, we have to say if there's a path of conversions that we can use such that the first letter of S1 or the ith letter of S1 can be converted into the ith letter of S2. So we pass it into BFS, which has our map dictionary, which tells us the different mappings that exist. And and then it goes into this function BFS. And here again, this is where the code isn't probably the most readable, but the functionality is basically this. I store a set of nodes which I say is visited, of letters which I say is visited. So I say, okay, I have already been this letter before. And then I create a list of, or this is also a set of nodes that I have to explore. So initially, I am K. I have to see what paths I can go from K. So from K, what all can I turn into? In fact, let's not use this example because the strings are equivalent here, but let's use this example, right? And specific, let's go for the second one, second letter. Okay. So I start with F, and my F is like a node which I have to visit. Okay. So I say while there are still nodes for me to visit, I'm going to create a new set, which was just for optimizing. I'm going to see, okay, what are all the characters I can become? So I can become F right now. Okay. Now, what are all the characters I can become from F? So from F, if we look at this, I can become T and I can become S. So I can become T and I can become S, right? And I check, okay, have I been T before? No, I have not. Okay, then that means I should visit this. So I put this in my to visit. And I do the same with S as well because I've not been S before. All right. And then so this is what this condition is doing. That is checking. Uh, so this LF condition is checking that, okay, have I already been this or do I already plan on being this character? If so, then I don't have to add it. But if it isn't, like if it isn't already covered, then I'm going to add it to the list of things I want to visit. And just before that, I also check that, okay, is this the character I want to be? So initially it's not because I want to turn into H, right? So I want to turn to H. So this is not, S is not H and T is not H. So I'm not done yet. Now, I say that, okay, I have now visited F. And so if anything ever points me to F, I will not go that way because that will make me loop back. So I've blocked F in a sense. Can never go back to F. And in my to visit, I have TNS. Now the loop restarts. I say, okay, I want to go. So let's say, I ask, what are my paths from T? So from T, I can become E, I can become F, I can become C. So E, F, C. Also, what's important is, okay, so E, F, C. But I can't be F because I've already been F. So I just remove this. I just don't add this. And then with S, I now repeat the same process. I ask, okay, what are the things I can become from S? From S, I can become H and I can become F. Now I've already been F, so I can't do that, but I can be H. And here, H is the target. So what my code will do is it will just return true. Now, eventually this program, if a path exists, it will find it. It is a breadth first search algorithm where it's saying, okay, can I go from F to H in one substitution? Then it checks, okay, can I go from F to H in two substitutions? So either through T or S. Then if that wouldn't have worked, it would say, okay, can I go there in three substitutions? So can I go further from E, C, and H, and can I get there? Eventually, if there is no way to convert, I'll run out of nodes to take. Like I'll end up at nodes, but any path leading to this will take me to an older node. And so, I can't actually go there. And if that happens, then the program will reach the end of this while loop and it will return false. That false will go back here, which will make it print no and say that there's no way to convert that string, and it will break. It won't execute further. And the way what I ended up doing was that, okay, if it doesn't break, so that's what this else condition does. If it doesn't break, then that means a path was found. That means this condition was true. So another way of doing this would just be, uh, sorry, yeah. So this was true, but also it was true for each position, which means it was true for each letter. And so if it never broke, then I can say, okay, yes, it is possible. I print yes. And this last else that prints no is just for the length comparison. And so that's a rough idea of how we can solve this problem. If we just stick to the high level idea, the point is go letter by letter and see if there's a way to convert this letter into this letter, this letter into this letter, this letter into this letter. If at any point I see that there is no way to do it, then I just say no and I stop. But if I get to the end and I never had to say no, then I can say yes. And the way we're implementing this conversion path is through BFS, or you can also use DFS, right? And that's how you could solve this question.